Alright, so for this problem we're going to be dealing with a pipe. We know the diameter of this pipe. We know the length of the pipe. This pipe is going to have a constant diameter, and we're going to have some sort of fluid traveling through it, and we will know the identity of the fluid, and therefore we're going to know the density of the fluid and the viscosity of the fluid. So those are all things that we know. And for this problem, we're also going to know the flow rate of the fluid. Or at least we're going to know that the flow rate that we're hoping to obtain. And so what we need to figure out is what driving force we have, what driving motivation we have for this flow rate to occur. And so we can look at the Bernoulli's equation for that. We have that the pressure at 2 minus the pressure at 1 over the density plus the velocity at 2 squared minus the velocity at 1 squared over 2 plus acceleration due to gravity minus the height at 2 minus the height at 1 is equal to the frictional heating. And we know that the frictional heating can be related to the fanning friction factor via this equation. So for this equation, for this situation, since we have a pipe of a constant diameter, the velocity at 2 and the velocity at 1 are going to be equivalent, and this whole term goes to 0. So that leaves two things as motivation for the flow. We can either have a pressure difference or a height difference. And height difference would obviously be obtained just by changing the height of the end of the pipe. A pressure difference would be achieved by connecting this to a pump system. So what we're looking for is what difference in pressure and or height is going to cause us to have a certain flow rate. And the combination of the pressure difference and the height difference is referred to as a head. And we can put this equation into a special form called the head form by dividing all the terms by the acceleration due to gravity. So we have the pressure at 2 minus the pressure at 1 over the density times the acceleration due to gravity plus the height at 2 minus the height at 1 over the acceleration due to gravity equals, and then we'll plug in this equation for the frictional heating, so that's -4 times fanning friction factor, and then there's delta x, which is the same thing as length here, so that's L, velocity squared. The velocity is a constant, so we don't need to determine 1 versus 2. And just for reference, 1 is this end of the pipe, 2 is the other end of the pipe, and we're assuming that flow is going in that direction. So, where were we? Alright, so then that is over 2 times the diameter times the acceleration due to gravity, because we divided everything by g. So that's the head form. And this part right here is the head. And that's what we're solving for. So we're solving for this head in relation to this q. But you'll notice we haven't included q in here anywhere yet, and we don't know everything. So we know we're looking for head. We can find the fanning friction factor, and we can find that, and we're going to use the Churchill equation. And the Churchill equation depends on the Reynolds number, which is rho v over mu. Alright. And we know the length, we know the diameter, and we know the acceleration due to gravity. And over here we know the density, the diameter, and the viscosity. What we don't know in any of these equations is the velocity, and that's what we need to find. And we can find that with our flow rate q. So we're going to have that q is equal to the velocity times the cross-sectional area. And for the circular pipe that we have that the cross-sectional area is pi d squared over 4. So then at this point we know q, we know diameter, so we can solve for the velocity and plug that in everywhere else. So have that the velocity is equal to 4q over pi d squared. And so at that point, we know everything in these equations, so we can calculate what head is needed for a specific flow rate. All right, so the next scenario that we're going to be dealing with is where we're still going to know the diameter of the pipe, we're still going to know the length of the pipe, the contents of the fluid flowing in, but we're not going to know Q this time. Instead, this time we're going to know the head. So this time we know the head and we're solving for Q as opposed to vice versa. So we're still going to use mostly the same equations. We just have to think about this a little bit differently because we don't know Q this time. So this time we're essentially going to be solving for the velocity because once we get to the velocity, we can solve for Q. And the velocity is in this part of the equation here, and it's also in the Churchill equation. Now, the issue is that the Churchill equation is nonlinear, and therefore it has a nonlinear relationship to f, so we're not going to be able to just solve for f and plug it in. So we're going to have to use a root solver in Python to solve this one. And so we can identify, what equations we're going to need to put into our root solver. And so first we have to think about signage. So our head right now is going to come out as a negative number. And that's because we're assuming that flow is going in at 1 and out at 2, so from 1 to 2. And that would be the same as either a height at 1 being higher than 2 or pressure at 1 being higher than 2. And since the Bernoulli's equation has it being 2 minus 1 in both cases, this is going to end up being negative. So the other way we can think about this is in terms of a head drop. And so a head drop is just the negative of the head. And so that would end up coming out as a positive number, which is a little bit nicer. So then we can plug that into there. These negatives cancel. And we've got that the head drop is equal to 4 length times velocity squared over 2 times diameter times acceleration due to gravity. But for a root solver, we're going to need to set this equal to 0, so we're going to subtract this over that side. We'll have the head drop minus 4 times fanning friction factor times the length times the velocity squared over 2 times the diameter times acceleration due to gravity is equal to 0. And so then that is the equation that we're going to end up putting into our root solver. The thing about the root solver is that it's going to take in a guess. And we have to have a guess that's sort of like in the right order of magnitude, or else it's not going to be very effective at solving it. So I'm going to put this over here. So we're going to need a guess for our flow rate. Which means we essentially need a guess for our velocity. But velocities could be a whole big range of things. Flow rates could be a big range, so it's hard to get an accurate guess. However, fanning friction factors have a very small range of values that it could be. So it's easier to get an order of magnitude correct if we guess the fanning friction factor. So we're going to guess the fanning friction factor. So we're going to have that the head drop. I'm just going to abbreviate head drop as HD, just to make it a little bit faster to write. So we're going to have that the head drop is, so that's going to be equal to 4 times our fanning friction factor, which we're going to put a guess in for, times the length times velocity squared over 2dg. So this guess, let's just say 0.01. So that's our guess for the fanning friction factor, and I just took that equation just straight from here. So we can rearrange this to solve for velocity because we also want velocity. This is our guess velocity. So velocity guess squared is going to be equal to, so that's head drop times 2 times diameter times acceleration due to gravity over 4 times 0.01 times the length. And then square root both sides, and we've got the velocity of our guess. So our guess velocity is equal to the square root of the head drop of 2 times the head drop times diameter times acceleration due to gravity over 4 times 0.01 times L. And then we can also simplify here. So that is going to be our guess velocity, which in turn is going to end up being our guess for the flow rate. So that's going to be this velocity guess times pi g squared over 4. So that's the guess we're going to put into our root solver equation. Alright, so first thing we want to do is we're going to be coding this problem. So the first thing is we're going to put in this Churchill equation for the friction factor. But before we do that, let's start by importing our libraries as always. So we're going to import numpy as np, and we're going to import scipy, from scipy optimize, we're going to import root. And those will be easily wrong. So we'll let that load. Alright, and then we can put in some of our constants. We know the fluid that we're going to have flowing through the pipe is going to be water. So our density is 1e to the third. Our viscosity, so that's mu, is 1e to the negative third. And then we also have our acceleration due to gravity, which is equal to 9.81. So we have those all in there. So now we can work on putting our Churchill equation in there. And we're going to define a function for that. So we're going to define the function, we'll call it Churchill. And this equation is going to need to take in, so let's look here. So we're going to need, so the Reynolds number, which is rho, and velocity, then, so it's rho. We need to have it take in the Reynolds number. We can calculate the Reynolds number elsewhere. So it's going to take in the Reynolds number. It's going to take in theta 1 and theta 2, which are defined here. And then within there we have this E over D term, and that is, we'll use one variable for that, just ED. And ED is a value of the roughness of the inside of the pipe. And then I think that's it. So within this now we need to define theta 1 and theta 2. So theta 1 is this equation here. So it's going to be parentheses negative 2.457 times np dot log. And we just need to do log because Python will default to a natural log instead of a log base 10. So that's fine there. So, and then another set of parentheses, so it's going to be 7 divided by the Reynolds number, and that is going to be to the 0.9 power, and then it's going to be plus 0.27 e times ed. So that parenthesis, and then the entire thing is going to be to the 16th power. Right. So then theta 2 is going to be equal to 37530 divided by the Reynolds number to the 16th power. All right, and then for this function, we're going to return this up here. So the important thing to know about this version of the equation is this is the Darcy friction factor. So we're going to need to multiply the friction factor by 4 to, because we're using the Fanning friction factor. And so when we do that, it will become f over 2 instead of f over 8. So, and then we're also going to multiply that denominator over to the other side so that we have that by itself, because that's what we're looking for. So we're going to have 2 times, and then parentheses, 8 divided by Reynolds number to the 12th, plus 1 divided by theta 1 plus theta 2 to the 1.5, and then that whole thing to the 1/12 power. Right. And then shift enter on that. That is supposed to be doing. Okay, there we go. So that's how we're going to put in our Churchill equation. Alright, so next we are going to work on the situation where we have no Q and we're trying to calculate the head. Or rather the head drop. We can do it in terms of head drop or head. Doesn't really matter. We're just going to get a different sign. So since we're using head drop for the second part of the problem, I'm going to use head drop for the first part of the problem as well, just for consistency. So we're going to define our function. We can call it head drop. And so what does this function need to take in? So what does it depend on? So it depends on f. It depends, but f we're going to calculate with this Churchill equation that we made. It takes in L. It takes in the velocity, but we're going to calculate that with the flow rate, but so we do need the flow rate. It takes in the diameter, and it takes in G, and I think that is all. Okay. So then within this we're going to return this equation, the head drop. So we're going to return 4 times F times L times V squared. Oh wait. Okay. In Python it should be, that's the 2 asterisks is the correct notation for a think I need this out of here, not the caret. So let me just take care of that real quick. Okay, I think we're good now. So the velocity squared divided by 2 times d times g. Right. So you'll notice we're getting red underline or yellow underlines under our f and our v, and that's because we haven't defined those yet. So we can do that up here. So easiest one to do is v because that's just right here. So we're going to have our velocity is equal to 4 times q divided by np dot pi times d squared. Okay. So then we need to define f. So f is going to be equal to, and we're going to use the Churchill equation to do that. So we're going to have Churchill of RE and ED. All right, so neither of those we've defined yet. ED can be something that we just take into this function. And then the Reynolds number, we can calculate it above. So Reynolds number is rho VV over mu, so that's going to be rho times velocity times diameter divided by mu. And so at that point we have everything fully defined, and we can shift up around that. And so there we have a method for calculating the head drop when we're given a flow rate. Alright, so third thing we're calculating is if we know the head and are trying to calculate the flow rate. So we're going to find our function first, and we'll call it flow because that's what we're trying to find. And I'll take in some values, we'll figure out what those are in a second. I didn't mean to shift enter, I just wanted to enter. So this is our function, and we're going to have to define a function within the function that we're going to take the root of. So we're also going to define just the equation we want to take the root of, so we'll just call that EQ. So the way the root solver works is it needs to take in a vector, and it needs to output a vector, and that is because it can be set up to solve multiple nonlinear equations at the same time. So it would take them in as a vector or an array, and it would also output them the same way. So this equation, we're going to have it take in some vector, and we'll just call it vector. So then we're going to want to return this right here, because this is the equation that we want it to solve. So we're going to have, we'll have HD for our head drop, and then minus, and then we have this value. And I could type that all in, or I could just use this head drop equation, or function that we already input. So I'm going to do that. And we're just going to copy and paste this up here, and paste it there. Alright, so now we're starting to see what we need to input. So within this vector, that's what's going to take in the head drop. So we're going to have vector is equal to head drop, and then we want to pull out the first, I have that backwards, hold it. Head drop is equal to the first term of the vector. So, and that's going to be our only term in the vector that we input, but we could input other things. We're just not going to, because we only have one, equation, one unknown. So, and then for these things, we're going to
need to input them up here. Well, I guess G is already defined, which technically means it doesn't need defined up here because we defined G all the way up here, so I'm just going to get rid of that here. And it should still work, so we can get rid of that here as well. And then, so then these things need to be inputted here. Alright, so then we have that. And so we now would like to return the root solver for this function within. Let's space that out so it looks nicer. So we're going to solve this with a root, which is going to set it equal to 0. So we'll return root. And within the root, we're going to first supply our function that we want to set equal to 0, so that's going to be the equation. And then it needs to have the vector that we take in. So it's going to be a vector. And so what we're going to take in is our guess. So it's going to be Q guess. Take in Q guess. Alright, so we're going to need to find Q guess up here. And so Q guess is equal to velocity guess times NP pi times diameter squared over 4. And then we need to define V guess above it. V guess is going to be NP dot square root. So then that's this here, and we've got the head drop times the diameter times the acceleration due to gravity divided by 2 times we're going to use F guess times L. I don't know what. Okay. And then we'll define F guess above. So F guess is going to be equal to 0.01. Okay. So then I think I have this messed up a little bit. So our head drop is going to actually be defined up here because that's what we're given in the problem. Sorry. So head drop will be defined up here, not down here. And then this is going to take in is Q. Yeah, so this is going to take in Q because that's what we don't know. I had it mixed up with this one up above. We do know head drops, that'll go in originally, and then this equation will take in Q, because that's what it's going to iteratively through the root solver, because that's what we're trying to solve for. So, I think it's all good now. Got the underline there. Not sure why. Let's shift that there and see if it works. Alright, so then The syntax error I have here is that I'm missing a parenthesis. And then I also still a Q input up here. So now everything should be good. So these are functions, and so we need to test if they work. So I have here values that we can use to check if they are calculating everything properly. So the first one is for our Churchill equation, so we're going to put Churchill, and we're going to put input a Reynolds number of 1600, and we're going to input a roughness of 1 e to the negative third, and we should get about 0.01, and we do. It's not exact, but you know, that's pretty far out there, and there's round off error and such, so I'm happy with that. So next we're going to have our head drop. So this we need to input the length, which is 10, input a flow rate, which is 0.1, next is diameter, which is 0.1, and then our roughness, which is 1 e to the negative 6, and we should get about 9.24. And we do, so that's good. 2 for 2. So for the third one, we're going to do our flow, and this one is basically going to be the opposite of the head drop we just did. We're going to put input 9.24 for the head drop and get a flow of 0.1, hopefully, as opposed to when we input a flow of 0.1 and got a head drop of 9.24. So this one for our length is 10 still. Diameter, we're still going to be 0.1. Roughness is 1 e to the negative 6. And then our head drop is going to be 9.24. Right. Okay, so here we've gotten the results of a root. And so the only value we really need is this x here, and we do see that is about 0.1. But we can, if we put dot x here, that will just take the x attribute like that. It's still within an array because it's a root solver, so it's going to output things as arrays in case we had multiple values we were solving for, but we're only solving for one variable, so we can take the first value out of there. And there we go. So that is how we would solve these kinds of problems using Python.